Hey everybody, welcome back to Black Guy Does Physics. Today we're going to knock out a problem by that Adriana D asked us to do, and this is, I think, 2014 Physics C number 1. So let's get it cracking. Let's see what's popping with this problem here. Once again, for every problem that you see here, man, you just simply want to make sure that you look at the diagram first and then try to prime your brain. Every time I talk about priming your brain, you're just priming it, making it ready to read the question. I see the question. All I see is a spring being compressed, so automatically my concept here that I'm dealing with is energy. Off rip. I know it's energy. It has to be energy. No matter what they're going to say, once I see a spring, it's energy. It is energy. Now, also, you might have some motion involved. And the reason why I say that is because there's a track with some distance on it, and it's a photo gate. For those of you who don't know what a photo gate is, it's just a fancy timer, man. All it does is just takes the time at specific intervals. So energy and motion, and I'm good to go. So I could also make sure that I know the relationship between energy and motion, and that's like, let's see here. You could do the kinetic energy, right? You could get the speed from the kinetic energy, and you could use that for if you want to do a motion problem with time in it or something to that effect. But usually, if you're dealing with motion, they would mention some time in there. But we definitely 100% know that it's energy. All right, let's read. In an experiment, a student wishes to use a spring to accelerate a cart along a horizontal level track. So I go and I underline horizontal level track. The spring is attached to the left end of the track as shown in the figure above and produce a nonlinear. So for those of you who don't know what nonlinear is, it's not like, okay, it's a straight line or so. For nonlinear, that's funny. I've heard kids tell me that it just means straight line. Nah. For regular spring, the spring force is F is equals to minus kx. So if you plot F versus x, what happens is that you end up with a straight line due to the fact that the force and the displacement of the spring, they're directly proportional to each other. So that's what linear means. When something is linear, it just simply means that it's a one-to-one relationship. You see, it's a power of 1 here and a power of 1 here. It's just a one-to-one relationship. So that's what it is. So if you look here, they said that Fs is equals to As squared plus Bs, which simply means that F isn't directly proportional to S or X, if you're confused about that. Okay, cool. Once I see F being written in terms of something else, automatic, it is, I know I have to go into calculus. Usually integration, automatically. I know I have to do this. Where S is the distance of the spring compressed in meters, a measuring tape is marked in centimeters, is attached to the side of the track. Students place 5 photo gates on the track at the location shown. So I see that students are placing things. That simply means that this should lead into, I think, an experiment, most likely, because I see students involved here. So that. All right, let's see. There are no numbers given there. Henceforth, I know they're going to ask me, hey, you should write it in some crap. Just integrate, man. Just go with your thing that you have there. So let's see what we have. Derive an expression for the potential energy U as a function of the compression S. Express your answer in terms of A, B, S, and S as a fundamental constants as appropriate. This junk that they always talk about, it's the same thing every single time. So let's see. Now, if they're just asking you for the potential energy, you must remember some facts. And I'll write these facts down. I'll scribble them. What is true? You should know that the potential energy is just equals to the work, or the negative of the work, I think. The change in the potential energy is equals to the negative of the work. In other words, it's just F times X. But because F isn't proportional or F is changing with X or something, you know off rip it's just F dot dx or S in this case. So what you're going to do, you're simply going to integrate F, and I think from where it starts, which would be 0, to where it's compressed, S. Oh, dope. So let's go. So that gives me the integral of AS squared plus BS. Let's see if we could get this going. So when I integrate this junk, I bring up, raise this power plus 1. So that gives me s cubed. And I divide by the power that's there. Remember, for integration, it's just rules, man, basic rules. And if you go to the top of the page, or the top of your exam when you're in the exam, they'll have the rules there. Just try and follow them. But don't get tricked, don't get nervous. Why? Because if usually in most of the cases, if you just show basic integration skills, they'll give you points. And all we're trying to do here on all these AP tests is just amass points. That's it. Remember, you just got to beat the next person. Okay? Just beat the next person. And we repeat the same thing. We add 1 to the power of s there, which would give me 2, divide by 2. Then we put our limits, and it's from 0 to s. And for those of you who don't remember or don't understand this, it's basic integration. When you have the limits here, you're going to input the value. It's the top one, this one. This one, let me put it in red here. It's this one minus this one. Okay? So let's see if we could get that here. We have, let's erase that. Let's go back into black. Come on. There we go. It's 0. If you put 0 in here, then everything disappears. So you just straight up as cubed over 3 plus bs squared over 2. No? Did I do it or wrong? Oh, Adriana is here with me. She's giving me instant feedback. So I was like, oh, what's she talking about? Did I do this wrong? I'm like, nah. Okay, good. Clutch God. All right, so we have that, and we should be good to go. Did I leave a negative sign out? I think I left my negative sign out. I might be wrong on this, but let's put it there. Great. All right, that's done. Great, let's go on. In a preliminary experiment, the student pushes a cart of mass 0.3. So once again, I underline what is there if I don't want to write it on the side. So I could write m is equal to 0.3 kilograms into the spring, compressing the spring 0.04 meters. So now that's my S or X of 0.04 meters. I could underline or I could write it down. I would suggest that you write it down on the side. For this spring, A is equals to 200 Newton per meter squared. So once you see this, oh no, that's not right. And B is equals to 150 Newton meter. The cart is released from rest. I underline that. And I know from rest, V0 is equals to 0. Assume friction and air resistance are negligible only during the short interval when the spring is accelerating the cart. Calculate the following. The speed of the cart immediately after it loses contact with the spring. Come on, AP. You really going to ask us this? Easy peasy, nice and cheesy. Let's go. It's what? It's a conservation of energy. Remember when we looked back and we wrote energy? We saw that our thing was energy. And what is true about energy? For energy, I'm going to write it down here to make sure you remember. For energy, what is true is that the energy is conserved. So the energy you have in the beginning is the energy you have in there. And for my students, I always write this long-ass equation, which is like your potentials, which is your gravity, your spring, your kinetics, both of them, and work being done by a non-conservative. It's just a constant. So all you have to do is check at the beginning and the end. So if we check at the beginning, we could see here that the only type of energy that is at the beginning would be the spring potential energy. So that would mean that's my spring potential energy. And at the end, the block is just moving because there was no friction or anything being done. It's all negligible there. And it's not vertical, it's not rolling, it's not doing anything. So therefore, that should just be the kinetic energy. Right? And then you just substitute here. So your spring kinetic energy, the spring potential energy you already found, which was AS cubed divided by 3 plus BS squared divided by 2 should be equals to half MV squared. And solve for V, which should not be that difficult. You could do that on your own. If you need help with that, let me know. But you could do that on your own. I don't have enough space for that. Good. You're in an AP class, man. A is for advanced. Let's go. The impulse given by the cart of the spring. Okay. So here, a lot of students might make a mistake right here. Why would they make a mistake right here? Is because I'll put it in red so you could see. Let's see. They're like, okay, it's an AP class and I have to do impulse. And the first thing that would pop in my head is that, oh my God, the impulse, I think the symbol for impulse is J. The impulse is equals to the integral of f dot dt. I'm big brain. Nah, bro, you want to make sure that it's the easiest thing you could do. You also need to write down the other one. What do you know the impulse is? The impulse itself is also equals to the change in momentum. That is also true. So if you know what the initial velocity was, or the initial velocity was, which was 0, and you know what the final velocity was when it released off it, then all you have to do is find the difference. So that means I have to go back to part 1 and actually calculate out what V is. Let's see if I could do that. So what's V? I multiply by 2. Multiply by 2 on both sides, get rid of that 2, and take this, divide by m square root. So I could just do 2 over m times as cubed over 3 plus bs squared over 2. And I take the square root of all of that. And that would be my V. So if that's the case, all I would have to do now, if I wanted to find out the impulse, is just do the change in momentum, which just be m delta v. So v minus v0, where v0. So I just multiply that. So that just gives me 2 times whatever is that. Oh, I forgot. Look at me being a muumuu. Don't be a muumuu. They gave us numbers. Because I was like, why would AP let us do all this crap? So just punch the numbers in from what they gave you. They gave us A and they gave us B and they gave us, yes, they gave us A and B and M. Oh, crap. See, that's why you need to write down the stuff that you have. I didn't write down the stuff on the side, and now it came to bite me in the butt. Okay, let's go. But you could fill that in. In the interest of time, I don't want to punch these numbers in. I'm pretty sure you could do this. All right, cool. Let's keep it moving. In a second experiment, the student collects data using the photo gates. Each photo gate measures the speed of the cart as it passes through the gate. The student calculates a spring compression that should give the cart a speed of 0.32 meters per second. After the cart loses contact with the spring, maybe I should have underlined this before I move on. This is the speed that it needs to give the cart. After the cart loses contact with the spring, the student runs the experiment by pushing the cart into the spring and compressing the spring the calculated distance and releasing the cart. The speeds are measured with precision of plus or minus 0.002 meters per second. The positions are measured with precisions of plus or minus 0.05 meters. So for the gate, okay, once I see this junk right here, I know that I have to graph. Without even seeing the graph thing, I know I have to graph. And the things that you need to remember for graphing are, 1, you better label with units. Also, you have your units. And make sure that you use a lot of the graph. I'm running out of space here. Oh, crappy penmanship. Oh, well. So you label. On the axis below, plot the data points for speed v of the cart as a function of x. Clearly, scale and label all axes as appropriate. Oh, crap. Thank you, AP. You're so kind. What is this? So that means you just put x, v. You remember, you put your units. I'll put them here. The units of v is meters per second, and the units of x is meters. And you're literally just plotting. Wow. Impressive. So that's 0. Let's see. The car speed, it goes from 0.412 or 0.33 to 0.3412. So you have to, that's 1, 2, 3, 4. Okay, so let's see. We're going to make each one of these 1, 2, 3, 4, 5. So let's make this. What do we want to make this? Scaling. I want to make it as big as possible, but it's 0.412. That sucks. Why didn't they give us that on the V? Okay. All right. Let's see. Can't be 0.1. So let's make it 0.2. So this is 0.246810. Nope. 4, 8, 12. Okay, so this is 0.2. Oh, I know how to fix this. Look at me being a moo. I start this from 0.1. Let's do that. So this would be my 0.1. 0.1. Great. So this is my 0.1. And this is my 0.2. This is my 0.3. And this is my 0.4. Hey, fixed it. Awesome. And now let's look at the positions. We go from 0.2. We have 1 to all the way to 1. So that's 1, 2, 3, 4, 5. So this would be my 0. That would be my 0.2, 0.4, 0.6, 0.8. And this would be my 1. So now I've filled up. And notice I did a trick where I start the x-axis down, but I have to label both of them so I would have more space. And I literally just plot. Once again, interest of time, don't want to, but I think for the next part you need to see what the graph is doing. So let's plot. 4.12, so 4.12 and 0.2 somewhere here. Remember, you don't have to be extremely accurate when doing this. It's a rough plot, man. 0.47 somewhere here, and 0.4 somewhere here. 0.39 and somewhere here, and 0.3, so that's 246, 247 somewhere here. Crap. And 1 is 0.3324 somewhere here. And you could see the trend. Oh, they don't want you to do anything. You just want to plot the points. So you can see a trend going on there. Good. Let's move on. Compare the speeds of the cart measured by the photogate 1 to the predicted value of the speed of the cart just after it loses contact with the spring. Okay, let's compare. For photogate 1, the speed is 0.412. Crap. But it's supposed to be 0.320. So let's see what the value of the speed predict. Okay, that's not too bad. Thank you. What it is here, the speed is higher. Than predicted. Cool. Then why would it be? How could you get a faster speed? Well, this is where your basic understanding of conservation of energy. If I compress the spring more, that means that there's more energy input in, more work is being done on the spring, which means that there's more energy in the spring. That means that more energy from the spring will be going into kinetic energy. So the spring was compressed more. The spring more than it should. That's nice and easy. From the measured speed values of the cart as it rolls down the track, give a physical explanation for the trend observed. Okay, what did we observe from here? Oh, the speed was decreasing. Remember, if it's a level track, the speed was supposed to be constant. And you cannot let AP trick you like this, man. If you see that there's some decrease in speed rolling over a table or something, then you know automatically you have some friction being done there. That's one. So we see the trend. Let's say what the trend is. The speed decreases when it should be constant. So you put that to make sure they understand you know exactly what you're talking about. You sound fancy right here. Should be constant. Look at you. Big brain in it. Let's go. And then you just say, there is friction. If you want to keep it simple. Or if you want to be real fancy, you just say something like, the track isn't level. Has an upward slope. Upward slope. Or you could even say, oh crap, let's go. It's inclined upward. Like it. And that should give you points. Now, if that don't give you a 15, you should get at least a 14, 13. And remember, a 13 or 14, you still Gucci. You still Gucci. Well, that's the end of this one. Hopefully we knocked it out of the park. If you have any comments, like, subscribe, leave some comments. And remember, everyone, don't be a moo-moo.